Okay, this slide show a illustration of difference between so-called positive and negative pore pressure. What we usually deal with in practical problems is so-called positive pore pressure. That is a pore pressure generated like a hydrostatic pressure that is defined as a unit weight of water multiplied by the depth. However, some materials are recognized as unsaturated materials that generate generation of so-called negative pore pressure can be an option, but this negative pore pressure is not a really practical issue when you're dealing with a real-time problem. So when we're talking about pore pressure, will always be uh, concentrated on so-called positive pore pressure. The positive pore pressure is hydrostatic pressure, and it's also the excess pore pressure that we discussed about last slide. This is an illustration of groundwater conditions during the construction of one trial pit near the river. When we have this gravel-like materials, that is usually full of water, since it's had quite large permeability coefficient, so we can see the conditions in the soil are being like this. How do we measure groundwater level in a borehole? That a very simple illustration is given by this uh, so-called open piezometer or observation well. Uh, what's the construction of this piezometer observation well? But it's very simple construction. You perform a borehole and then install this uh, plastic or steel pipe that is perforated at the bottom. It has stopper at the bottom, but here is some space for the water to enter this pipe. As the water enter the pipes through these perforated parts, it defines some water level in the borehole. What we need, well, we need some equipment to measure where is that water exactly. Is it here or here? Or is it maybe here? But this is very simple piezometer equipment that is used. So we have this probe that is connected with the readout unit at the bottom by this measuring tape. And we can measure here at what depth this probe reaches the water. When this probe reaches the water surface, it sends us this light and sound signal to this readout unit, and then we can see at this tape how deep is the contact between the probe and the water. That defines the groundwater level at this observation well. It can be performed not only in the case, it can sometimes be performed in an uncased borehole if it's not failed, if it's stable, the open borehole. This is very simple and cheap technique for measuring water level. It's very often used in local practice, but it can really be used only when the groundwater regime is known. So when we have some question how could the water seep in the soil, then this technique is very very no, it's not appropriate. It's not appropriate. Why? Because maybe we have here some layer of the unpermeable soil, and we have some water level here. Down below we have maybe some other permeable soil with some water streams, but this way we'll have this water from uphill coming down. So this is not appropriate for measuring of the water. That's why what we usually use in practice is this so-called Casagrande piezometer construction. It's similar to this observation well, but the main difference is here. Up above this filter part, this is a steel or plastic pipe that is perforated, or it has this filter filter stone at the bottom that can enable the water to get inside this pipe, and all around it we have a sand material. So this is filter sand material, but above it we have this unpermeable bentonite grouted part. So we protect the water from above of the borehole to go down, and then we exactly measure the uh, pore water level at this point where this filter part is located. The negative aspect of this piezometer, it that is relatively slow react on any groundwater level change from here to here or something else. It is usually used to measure the water level in predefined depth. So if you want to measure here or some other depth or somewhere else, that's where we define this permeable part. Up above it, we do this routing to prevent the water from higher level reaches down. So we only measure the water regime in this area. The good thing is that these piezometers can be installed in multi-level. So we can install in one borehole not only one pipe, we can install 2 or 3 or more pipes, like here. We have 1, 2, 3 pipes linked one to each other, but this perforated pipe is located at different depths. For example, we have perforated pipe part here, here, or somewhere up, and then we put all the installation in one borehole, and then around this pipe we pour it by sand. Up above it we pour it by grouting mixture, and again sand, and then grouting mixture. So we isolate these parts where we want to measure groundwater level. This is something that is most often used in the local practice, but worldwide and sometimes in local practice there exists a lot more different advanced kind of piezometers used for measuring pore pressure, and for solving this main problem is a slow reaction on groundwater level changes. For example, it's hydraulic, pneumatic, vibrating wire, electric, multi-point puckers, and so on and so on. Different kinds can be of piezometer can be found as commercial. They are selling worldwide, and they are sometimes used in local practice as well. Uh, an example of advanced piezometer that can be used is this electric piezometer that can be used for measuring water pressure. It's actually similar to this Casagrande piezometer, but the pore pressure here is not measured by inserting this probe. Actually, it's continuously measured by the change of electric resistance of this measurement unit, since this piezometer unit is connected by cable to the readout unit located at the surface. So we can, in any moment, in any time, we can collect the data about pore pressure in soil. Similar things are value are appropriate for pneumatic or vibrating wire type piezometer. It can also be installed in multi-level. You can place one this probe here, the other probe here, connected by cable to the readout unit, and collect the data in any time. So this is the main advantage of these piezometers. Okay, most of this equipment shows in the previous slides, like inclometers, piezometers, soil samples, and some additional monitoring techniques will be now presented in one case study, practical example, where we have a problem occurred after the highway construction. The problem was found to be as these cracks concentrated here, here on the opposite side, here uphill at this local road. Everything indicated that some sliding was happening next to this existing highway route. So the location is here at the central part of the Bosnia and Herzegovina. This is the photography from here, and these are the conditions at this location. What is important to note that this location is not first time recognized and as a problem. And 5 years ago, it's known problem from 1960, 1970, where Professor Sarac Jovanovic performed plenty of investigation work to define the sliding mechanism of this area, since the regional road passed this similar area as this new constructed highway route that you can see here in the condition as it is today. Once again, at the bottom, we have a Bosnia River basin. So the river flows down, and it's sometimes here near this edge of the water that can definitely influence the stability of the toe area, to influence the stability of all the area above. When we look at the some information known about this landslide from the past, Professor Sarac and Jovanovic mentioned the potential sliding at the depth of 16 to 20 meters. So it's very, very deep landslide, and any sliding at this depth, of course, it will need plenty of support measure to support this if it is really potential problem for this highway construction. At this moment, when these cracks are first time recognized here and here, only the remediation of the surface of this pavement was performed by cutting this and replacing it with some new layer of pavement, and then it was flattened and it was continued to be used. But of course, some measures had to be introduced to, to have this under control, not to have some unexpected problems like a sudden increase in the displacement that could stop this highway route. When we look at the information from the past, we could find that this landslide area consists of different kinds of weak rocks like marls, sandstones, clay stones, and siltstones. The problem is that the rocks are layered with unfavorable bedding planes. That means if you look at the cross section and you see the rock, it's bedded like this. So the potential sliding could occur down to the rock material, not only at the contact between this soil-like material and the rock. This topsoil material is made of typically some sandy clay material that can be found near the surface and 2, 3 to 5 meters at the top. Uh, 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 this is the location of this area near to the river. So here, over here, you can see what this river do with some increment and decrease of the water level. The things like this are very often down here, so this can influence the condition of the highway route up above. Also, up above the hill, you can see some local sliding here, and it's not unusual that you have some sliding here at the local condition. Of course, this is not related to these cracks observed here, but it shows that all this area is really prone to sliding. This is, for example, typical slope observed during the terrain visit 2015. So when it was constructed, it started the construction 10 years ago, then it continued 9 years ago, 8 years ago, it was practically all finished, 2013, and then at the end of the 2014, the cracks observed at the main road, some useful information on displacement could be also observed, and the local road, the local road is down the hill between highway and this river. Also up above higher at this regional road, some crack could be observed, and everything indicated that some sliding could potentially be in this area, since the cracks are found here and here. So what was done in the with the idea to monitoring this, to try to understand this area. Why is all this happening? Well, plenty of works were performed, including the visual observation, the borehole drilling and collection of samples for laboratory tests, a geodetic survey with plenty of fixed points installed to follow its displacement in time. The piezometer were installed to measure pore pressures, and inclinometers were installed to measure lateral displacements along the depth of the potentially unstable area. So here are cracks. Observe cracks at the highway. So this is one road. This is the other direction. This is the local road. Here is the river. And up above is this regional road. And this is uphill area. Over here is hill and down is river. So this is typical cross section from the middle. And these all points indicate the geodetic survey points. Inclinometer is located, one here, the other here. The one is in the stable area, just to see if there's some difference between this potentially unstable and stable area. Piezometers here. All the measurements were concentrated in this typical central cross section to define it as more as possible. So what was done as a practical measure during this investigation is that the allowable speed was reduced to 80 kilometers per hour. The visual observation were continuous, and you can see some cracks here. These cracks and these cracks are local road. The comparison of the conditions at the spring, at the at the winter and at the spring, you can see that some increment in this spacing between road and this sidewalk is definitely visible even by visual observation without some special measuring techniques. The investigation works, boreholes confirmed the information given by Sarac and Jovanovic. So it's a top soil layer 5 or 6 meters, followed by different types of sedimentary rocks like marl, sandstone, that are really like this bedding plane are so much defined, and sliding really could occur along these bedding planes, not only at the contact between surface soil and this weathered rock. Typical cross section introduced these sediment rocks and about 8 to 10 meters of very weathered bedrock and sandy clay materials. This is cross section, this is regional road, this is highway road, this is local road, and down here is the river basin. The laboratory testings concentrating on defining strength parameters. The strength parameters of soil-like materials are similar to the one reported from the previous literature. The geodetic survey indicates no significant displacement in the first year of the measurements. After that, during the winter, the snow cleaning in the winter part, all of these fixed points were actually destructed, so it was not possible to continue monitoring on the second, third, and 4 years after the installation. But initial readings show no significant displacement observed in the first 1 year period of monitoring. The groundwater pressure measurements were recorded by multi-point Casagrande piezometer or Casagrande standpipe piezometer and electric vibrating wire piezometer installed in multi-levels. I won't read all the results now in the detail, but when we get back to this typical cross-section, what can be concluded that the pore pressures are concentrated here at uptill, at practically at the ground surface, and then it follows down to some depth of about 10 to 12 meters below the highway. So this is some typical groundwater level observed after all these measurements. When we look at the inclinometer casing, this is the inclinometer casing installed in this borehole just below this embankment of the highway. Some increment in displacement occurred at the depths between 16 and 18 meters. The displacement is around 5 millimeters, so very small displacement were observed in the period of about 6 month measurements. What I didn't show here are the results collected later, maybe during the last 2 or 3 years. That's after 4 or 5 years measurement after this. This line eh, become to increase its displacement, and the results looks like here, like 10 or 15 millimeters, indicating that the displacement is very, very slow. So this is one so-called creep slide more than a landslide, where you have about all 5 centimeters per year. So very slow creeping observed here, and that's why it still work to just change the pavement after 1 or 2 years when the cracks, small cracks observed, were found at the surface. And so far, actually nothing performed here as a remediation measure. Of course, some preliminary designs were performed, but it showed that really a lot of effort, money, and energy must be performed to stop any sliding in this area. So there are actually two designs for this uh, slope. One is a so-called a group of just a preliminary measure to reduce the probability of sliding, and that consists of construction of sub-horizontal drains in this area. So the idea is to collect as much as possible water here in this area of high water level, to collect water by horizontal drains and collect water here and bring it out of this slope. Any other solution that will support all this measure with some large retaining walls and something are definitely out of option in this condition like now, where the increment of sliding is very, very slow. However, the monitoring is performed. Now it will continue to be performed every 3 months or every half a year, just to get an indication if some problem is about to occur. What is very important is the diagram of the time versus lateral displacement. If this diagram looks like this and it's all time the same increment, then it's not indicating some problems. But if some period this line becomes to look like this, then this is definitely a warning that some sudden increase in the horizontal displacement could be an introduction for some very, very big problem that could really stop this road from working. Okay, here are some other useful information collected by this geologic camera, where one of the inclometer casing were stopped working since this probe could not pass this pipe. And then when introducing this geologic camera into this borehole drilling, it was found that this plastic pipe, was totally broken at the depth of about 10 meters. And since this borehole is located uphill here, it really consists well with the depth of the sliding area that is in around of 16 meters from the top, since this part is actually excavated for this regional road construction. Some discussion on the results and interpretation shows that there was really little displacement during eight-month monitoring in this first period, but later it was shown that some increment of the horizontal displacement occurs at the depth of about 16 meters, showing that the increment of displacement is very, very slow, indicating that we are talking about sliding, creep slope that can be controlled by monitoring. And if any sudden increase of horizontal displacement occurs, it's necessary to introduce at least these measures to reduce the possibility of sliding. Of course, the measurement continuing, the measures always performed after heavy rainfalls and snow melting. Okay, this last part of this uh, second part of presentation is now predicted for some discussions. If you have some similar experience of this kind of landslides, maybe you can share it with us. What do you think about this case study? What is your opinion? What would you suggest as some useful proposal? And do you have some design solution maybe to solve this problem and to stop thinking about it, or maybe do you think it's better to continue living with this landslide, and if something interesting is measured, something new information is gained, maybe then we can start and performing some expensive supporting measure. Do you have some comments? Would you like to add something, or
I have a
okay?
question.
Yes, okay.
Uh, since we know the number of boreholes needed for one landslide, how can we know the depth of that borehole? Because in the longitudinal section that you showed in the first slides, there were some boreholes deeper than the other. So how can we know the depth of the borehole?
Well, in the landslide area, well, the depth of the borehole always have to reach the stable area. So if we drill a hole here, it, if we just stop the borehole here before we reach this line of the, let's say, good material, rock-like material, then this borehole is really not useful. It doesn't use to anything. So we always need to drill the hole down to the material that is not prone to sliding. For example, well, it's just usually enters this good material for, let's say, 2 to 5 meters. Here, it was a much bigger problem. Here, not. Here, really, this is soil-like material in the 20 meters, and then you have a very quality rock similar to the one you see here. Practically, this is the soil profile you have on this landslide. There is 20 meters of the soil like this, and then you have a rock. It's more than obvious that we have sliding here, if the sliding really is an option. So at the contact, but a very bigger problem was here. When you have something like this, then we are not sure if the sliding occurs here at the contact of this soil-like material and this rock-like material. And this could be a huge problem. We could build, for example, inclometers that are, let's say, 10 meters deep. If we put inclometers 10-meter deep, then they will not be fixed in the stable rock, and we will not get any useful information. That's why it's very good for this problem that we don't know that we don't know the depth of the sliding, to go very conservatively 30-40 meters with the borehole, to be sure that we'll have this fixed point somewhere. So when we construct the inclometer, it should go like this. Here it should go as deeper as possible. So typical guidance for the depth of the boreholes in the landslides: go and reach the stable area. The stable area must be defined in situ during the drilling operation. You can recognize it as a very, very large resistance to drilling. You can recognize it as a very good quality rock material like it's here. You can see this a very good quality intact material, not prone to sliding. So that's the main criteria in landslides. Pass all the potential landslide area and enter the solid, stiff material, not prone to sliding. Did I manage to answer you? Do you need any more clarification?
Yes, thank you. And I have another question.
Okay.
You mentioned piezometers, inclinometers, and extensometers.
Okay.
So briefly, the piezometers show us the pore pressure and the groundwater level, right?
Okay, that's right.
Uh, the inclinometers show us uh, the displacement
Horizontal
of the
displacement, horizontal displacement
horizontal. And
in depth, in any depth along the
yes,
borehole.
and what was the use of the extensometers?
Extensometer. Okay, let me explain this maybe on this problem. Here you can. I don't know what this. This not working. Not okay. Let's try this. if you apply inclinometer here, you'll get as a result the horizontal displacement. I don't get this. Let me try to start it again. Okay, just to share. Okay, I can share this screen. Can you see this now? Can you see this?
Yes. Yes.
Okay. So
Yes.
if you install the inclinometer here, you will measure the horizontal displacement along the depth. You're expecting to have horizontal displacement here, and then suddenly to stop having it here, since this is stiff rock. When you draw it, it looks like this. If you get back in 1 year again, you may get this. In 2 years, you may get this. So displacement are going more and more horizontal. So and if you install the extensometer, for example, here, not vertically, but in some sub-horizontal position, you have rings all around this extensometer. These rings are grouted and linked to surrounding soil, but they can slide along this plastic pipe that you saw on the figure. So if you have displacement now, if you have displacement of this point here, this also point moves here, this point, since all these points moves in this direction, you will not have any relative change of relative distance between the rings. But here, you'll definitely have this ring moves here, and this ring doesn't move at all since it's in rock. So you will have the position where the increments of the displacement occurs. I don't know if I'm clear, but let's back to this. Let's back to this. Okay, here. So you install this pipe in this sub-horizontal borehole, and you have these rings. Look at this. It's rings. It's magnetic rings. It's the purpose of this ring is that this probe that you passed through this pipe, it recognizes the spacing between here, between this and this. And if you have sliding here, then definitely the ring distance between these two rings will change as the soil moves. As the soil moves, this is how this rings actually moves. Since this string, you see, it's not fixed to this pipe. It can move. It can move. And as it moves, the distance between these two rings is changing. And then you can get the location where the sliding occurs. This is very important information when you know the depth of the sliding, the location of the sliding surface. So you can combine extensometer with inclinometers. You can only use extensometer. More often in local practice, inclinometers were actually used, and it's vertical hole that is, with plastic pipe grouted all around. But the principle is different. Here you have these magnetic rings. Why magnetic rings? Because these rings can be recognized by a special probe that you enter this pipe, same as inclinometer probe that is inserted in the inclinometer casing. As this why the spacing between these two rings is changing? It is changing because the soil moves, and the rings are connected to the soil by this grouting mixture, this water cement mixture that links the borehole with the ring. Okay, was it clear?
Yes, thank you.
Okay, thank you for your interest. Okay, we'll stop here, make a, let's say, one short break in 6 minutes. Now it's 15:19. We can go to 15:25, and then we'll start with this third part to try to finish this before 4 o'clock.